All righty, let's go ahead and get started. Well, today we will work some example problems, finish up discussing some of these Bernoulli style of questions. And that way, next class, we'll be able to start into the next part of fluids, which deals with Archimedes' principle and the pressure depth relationship and things like that. So just reviewing, what are the two big equations we use for this particular topic of fluids?
It's my bad. I thought you was asking. My bad.
Oh, no problem. The first one is Bernoulli, and that's the main equation. That's the big one. It's the one that says when you have a pipe system, you could measure information about one location in the pipe system and measure stuff about another location, and the total pressure, or the sum of all the terms which deals with pressure, will be constant no matter which location you look at. And the way it's written is that the pressure at a certain location plus a term about the speed of the fluid flowing in that location plus a term about the height of the pipe system is equal to the same, but in the second location. V2 plus 1/2 rho V2 squared. Oops, that's a P, not a rho. Plus rho GH2. And we remember, just like with conservation of energy, while the two sides of the equation equal each other, each term can change. And so it might be that the pressure on the left side is bigger than the pressure on the right side. And the reason is because maybe the speed on the right is bigger than the speed on the left. So each term can change, but what can't change is the total sum on either side, right? If you add up all three terms, maybe you get 100. Well, if that's true on the left, the same is true on the right. You're still going to get 100. But how you get 100 may be different. Maybe now the velocity term is bigger than it was before, thus the pressure must have been lower, or some such thing. So that was Bernoulli. And then the other one is a continuity equation that basically says the volume flow rate of a fluid, which is how much fluid flows per second, a gallon of water per second, or a liter of oxygen, whatever it is constant. And so if you have a pipe system, or maybe you have your blood vessels, blood's flowing through your blood vessels, and as it gets further away from your heart, the vessels constrict more and more. And so you would expect that the velocity in the more constricted parts of your blood vessels is faster, is larger than in the larger parts, like the arteries and the veins and things like this. So with these two equations, that's how we're going to solve all the Bernoulli type questions we have. And last time we did an example, and that example showed basically if you have a pipe system and you constrict it, how do we deal with it? But it did not have, I believe, the example we did not have anything about a change in the height. Okay, so we didn't deal with the full Bernoulli. We were able to ignore the height terms. Now, what I'd like to do, of course, is actually do a full example problem, one that has elements from each term. And so I'll draw the pipe system so we can see what it looks like. We'll have a pipe, starts here, and it's going to move along a certain distance, and it's going to maybe travel up to the second floor of a house, at which point it then constricts to a smaller pipe, and that's where it ends. Okay, so maybe this is a water pipe going from the kitchen on the downstairs up to the bedroom upstairs shower or something like that. And some of the information we know, firstly, is that the radius, R1, in the first part of our pipe, let's say is 10 centimeters. And the fluid that flows through here, let's say it's water, flows with a velocity V1 of 20 meters per second. Okay. Then the pipe will lift up to the second floor, which I will call, let's say, 15 meters above the ground. And the constriction makes the second part of the pipe, R2, equal to 5 centimeters. Okay. So that's our setup. We have a pipe system. The pipe is moving along. It goes up to the second floor and then constricts. And we know all the data we know here. And the question, of course, is to calculate the change in the pressure between the beginning of the pipe and the end of the pipe. So how do I go about solving something like this? Well, the first thing I do is I say, I know the equation I want to use. That's going to be the Bernoulli equation. P1 plus 1/2 rho V1 squared plus rho GH 1 is the same for 2. And then I will look to see, is there anything I can cancel? Are there any terms that are not necessary for this particular example? As you remember in the last example, the pipe didn't change height. It was just constricting, and that's all it did. It stayed straight. So I could ignore the height terms. So I look here and I say, okay, well, obviously the pipe does change heights. So I have to keep the terms with height in it. But what about the terms with velocity? Does the water change velocity in this problem? Anybody having an idea?
I would say when the pipe constricts, does it change velocity?
So you think it does change velocity?
Well, yeah, when it gets to when the pipe actually becomes smaller.
Okay.
Or,
Anybody else agree or disagree?
I agree.
Okay, well, you're exactly right. Perfect. Remember, even if the problem doesn't specifically say, oh, the velocity went from this to this or anything like that, when you see the fact that the pipe itself changes size, either it expands and gets bigger or it gets smaller, then that's a clue to tell you, the velocity is changing. So when I look at this particular problem, I see there's a constriction. And so, yes, I have to keep the terms with the velocity because I know the velocity will change. Now, I don't know the value of the second velocity. I only know the value of the first, but I do know V2 will be something different. And likely, I'm going to have to calculate it later. Yeah.
I want to know. I'm sorry if I missed. What are we trying to find with this diagram? Are we trying to find the pressure change?
Yeah. Let's find the change in pressure. And when I say that, I mean P2 minus P1. Okay. So that's the question. Find the change in pressure for this system from beginning to end. All right, so I know this is my equation, and I know there's nothing I could cancel outright, so I have to keep everything. So the next thing I do is I go ahead and I manipulate the equation to solve for it is the thing I'm solving for. In this case, I'm looking for P2 minus P1, so I want to move terms around here to get P2 minus P1 on one side and everything else I move to the other side. So when I see it, this particular equation, I say, okay, P2's over here. So let me bring P1 to the other side with it. And so now I have P2 minus P1 on one side. And then I have to move everything else. So this 1/2 rho V2 squared has to go, and the rho GH2 has to go. So I move them over to the left. And so what I'm left with is on the left side, or now my right side of the equation, 1/2 rho V1 squared minus 1/2 rho V2 squared. And then rho GH1 minus rho GH2. Okay. So I took the equation as it was, and on one side, I have P2 minus P1, which is the thing I'm looking for. And so I have to keep it by itself, which means I bring everything else to the other side. And of course, when you bring something to the other side, it changes sign if you're adding or subtracting it. Now, I will mention that sometimes what you'll see when people solve this, especially if they're fancy with their math, they want to show how fancy they are by showing, look, we have a term 1/2 rho V1 squared and 1/2 rho V2 squared. Well, 1/2 rho is common to those two things. So they'll just write it 1/2 times rho times V1 squared minus V2 squared. Okay. And then the same for the rho GH. Rho and G are common to those two terms. So I could factor them out, rho times G, and what's left over is just H1 minus H2. Okay, so either way, these are both exactly the same. It's just one is fancier looking. You've kind of cleaned it up a little bit by using some knowledge about algebra and factored out some like terms, and now it looks like this. If you don't like that, then just leave it the way it was before. There's no problem with that as well. But I'm showing you this because a lot of times if you're looking at other people solve problems, either on YouTube or in textbooks or things like that, you may see it look like this. And so if you wonder where the heck that comes from, it's just this kind of manipulation of the algebra, factoring like terms just to make it look a little cleaner. That's all it is. All right, so that's what I want to solve, right? I need all of these terms over here. If I know all of those numbers, I could just plug them in my calculator and I'll have my answer. So I asked myself, do I know all of these numbers? Well, rho, I haven't told you in this one, but we said it last time. Rho for water is going to be 1,000 kilograms per cubic meter. Okay, it's just a number for water. And so that's what we're going to use for rho. So we know what rho is. Perfect. Do we know the first velocity? That is the velocity at the first part of the pipe. And indeed, there it is, 20. So we know V1. V2, I don't know V2. Okay, so that's something I'm going to have to figure out. Rho, I know. G, that's 9.8. H1, do I know the first height? Well, this is interesting. I'm not told what the heights are. If you notice, in this problem, all I know is that it went up from wherever it started, it went up 15 meters. So I don't know the value of H1, and I also don't know the value of H2. I don't know what those numbers are. What I know is the difference. If I subtract H2 and H1, then I get 15 meters because they're 15 meters apart. So how do I handle this? Do I need to know the actual height 1 value and the actual height 2 value? Though the way I answer this question is I remind you of conservation of energy. With conservation of energy, we had, remember, gravitational potential energy. And I said, well, the amount of energy stored in an object depends on its height above the ground. And so if I have a rock in my hand and I lift it up, say I'm 6'5", so I lift it up 6 feet above the air, let's say. Well, it's got a certain amount of energy, which is equal to m times g times h, where h is 6 feet above the ground. And so when I let go that potential energy, as it starts to fall, the potential energy gets converted to kinetic and so forth. However, one thing I didn't mention is the fact that currently I'm in my apartment, which is on the 3rd floor of this building. So the rock is not just 6 feet above the ground, but rather 6 feet above my floor, and my floor is still another 20 or 30 feet above the ground. So shouldn't I have to take into account the fact that where my rock is relative to the actual ground level? Or is it okay to just look at the 6 feet above where my feet are? And the answer is all that ever matters is the difference. So if my rock is going to fall 6 feet, it doesn't matter if I'm standing on top of a mountain or if I'm under the water in the city of Atlantis, it doesn't matter. All that matters is I start at this location and the rock ends at this location. The difference between those two heights is 6 meters. And the same thing is true here. I don't care if this pipe system started in the Freedom Tower, 100 floors up in the air, and I'm going from the 99th floor to the 100th floor, something like that. All I care about is wherever I start, I'm going 15 meters up from there. And what this allows me to do is have a little bit of freedom in how I choose my heights. I have the ability to choose any height I want, as long as whatever I choose, height 2 is 15 more than height 1. So I can say, well, let height 1 be 10. So height 2 is going to be 10 plus 15, which is 25. Or the smartest thing to do is to make it as easy as possible. And so what would make this as easy as possible is to call height 1 0, because then the whole term with height 1 just cancels out because it's 0. And so height 2 is 0 plus 15, which is 15. And you can always do this for these problems. All you care about is the difference in height. Where you actually start, are you on the 20th floor or the 28th floor? It doesn't matter. So that tells me I'm going to make H1 0, and thus H2 has to be 15. Again, I could have called H1 10, and so H2 is 25 instead. And I'll get the exact same answer later on. Or I could call H1 152, and so H2 has to be 167. I mean, that's stupid. It's weird to do that, but it works, and you're more than welcome to do it. However, what I suggest to you is, since you have the freedom of choosing the numbers, always choose one of them to be 0, and the other is whatever the difference is. In this case, it happens to be this 15 here. And that'll allow one of the terms to drop off. It just makes the math a little bit faster.
So I got a question. What's if, let's say the problem is in reverse, meaning let's say the pipe went down 15 meters. Would H1 be still 0 and then H2 would be minus 15?
Good. Yeah, you have a choice. You can say, okay, here's H1 and here's H2, right? And I know this difference is 15 meters. What I can do is I can either call H1 0, and so H2 is negative 15. That works. Or I could say, well, the lowest part I will always call 0. So I'll call H2 0, and so H1 was 15. That also works. You're welcome to choose any numbers such that you follow whatever this rule says. The difference between them is 15 meters. So if I call H1 15, then yes, H2 is going to be 0. If I call H1 0, H2 has to be 15 less than that, which would be negative 15. Perfect, exactly right. Here, it's a little bit more clear because you're going up, so you avoid the negative stuff. But it does bring to mind, I could have called this up here 0, and so H1 would be negative 15 here. That would have worked too. But of course, that's a little weird. You want to avoid negatives whenever possible. So I call, what I usually do, and I do the same in conservation of energy, I usually just look at my problem. Whatever the lowest part is, I call that height the 0, and everything else is something else relative to that 0. That way I'll always have positive heights and I never have negative stuff.
Okay. So pretty much, okay. I see what you're saying. So it doesn't matter if it was in a negative situation, it doesn't matter as long as 15 is in a negative situation is 15 has decreased in height by 15 meters.
Yeah.
Okay.
Right, exactly. So like this one, as I said, if you called the height 1, which is the highest part 0, then the number you'd plug in for height 2 would be negative 15 because it's 15 less than whatever height 1 was, which was the rule given by this particular thing here. Yeah, perfect. Any other questions about this height business? Because I see it a lot in previous semesters where people will say, well, you didn't give us a height in this problem. How do I know what numbers to choose? And the key here, I mean, I could give you a problem where I actually give you the actual values of the height, and then you just plug those numbers in, no big deal. But usually what you'll find is you have this situation where I don't tell you the heights, but I tell you how it changes. The pipe went up 15 meters or it went down 20 meters to the basement or whatever the case is. And if you have that situation, it's actually better, even though, you know, it seems like you're missing some stuff. It's better because you have the freedom to choose whatever you want. And so you'll usually choose numbers that make this stuff as easy as possible. And what that means in this situation is one of the heights you call 0, so the term drops off, and the other one is whatever this number is, which happens to be 15. All right, well, given that, I now know I have all the information I need except V2. I don't know how fast the fluid flows in the second part of my pipe. However, if I know that number, if somehow I can calculate it, then I'll have everything I need here, plug it all into my calculator, and I'll get my answer. So I'm now at a point where I have to calculate V2. So I forget about Bernoulli for now, and I go over to continuity. I say continuity equation, A1V1 is A2V2. And I'm going to solve this for V2. So I divide A2 over. So I have V2 is A1 over A2 times V1. That's the equation I have. Now I can start plugging stuff in. I remember area here for area of a pipe means the cross-sectional area. That is the area of the opening, the hole in the pipe. And so that's a circular opening. So the area is pi r squared. So I have pi r1 squared over pi r2 squared, all of that times V1. And then I say, do I know all of these numbers? Well, first, notice the pi's cancel out. And the pi's will always cancel out. Okay, so sometimes people will write the equation without the pi in it. Just the r1 squared times v1 is r2 squared times v2, but then it's confused. Where the heck are you getting r squared? What is r? But if you see it's pi r squared, you know, oh, that's the area of a circle. That's where this term is coming from. That's why I always write the pi, even though they cancel out every time.
Wait, how did you figure out that it was going to be a circle?
Yeah, so if you think about a pipe, it's like that cylinder, right? So here's the pipe here. That's what a pipe looks like, let's say, a normal pipe. And so when one says the cross-sectional area, what one means is, what is the size of this opening? The opening in the pipe. And so if we turn the pipe to look down the pipe, what you see is it's just a circle, right? And so the fluid is flowing through, you know, down into the circle that way through this pipe. And so what you want is the area of this opening. And the opening is a circle because if you look at a pipe is a cylinder and the opening in the pipe is circular. So, and I know the area of a circle is just pi r squared. So if I want the area of this pipe, it's pi times the radius of that part of the pipe. Okay, so does that make sense?
Yes, thank you.
Good, good. All right, so now all I have to do is plug numbers here. Do I know all of these numbers? Of course, that's always important to ask oneself. So I say R1, do I know radius 1? Yep, here it is right here. Radius 1 is 10 centimeters. Ah, centimeters. This is bad. Physics, again, and all sciences, whether you're doing biology, chemistry, physics, doesn't matter. You always have to make sure you're using the right units. If you use wrong units, your number is going to be off. And I know that for physics, we have determined that the units we always use are going to be meters for distances. So I don't like 10 centimeters. What I like is 0.1 meters. I have to convert centimeters to meters. So it's 0.1 squared. And what about radius 2? Radius 2 is 5 centimeters. Okay, again, centimeters is bad. I have to convert it to meters. So it's 0.05 meters, and that's squared. And then I need V1, the velocity in the first part of the pipe. There it is, 20 meters per second. So this is 20. And so now I just plug this into my calculator. So I say, okay, 0.1 squared divided by 0.05 squared, all of that times 20 gives me V2 must be 80 meters per second. And then as usual, before I actually use this number, I ask myself, does it make sense? Because I may have made a mistake here. Maybe I switched R1 and R2 or something weird. And the way I always ask myself this is I look at the problem, I say, V2, should V2 be bigger or smaller than V1? How do I know? Well, how does the pipe change? If the pipe constricts, the velocity should go up. If the pipe expands, the velocity should go down. Well, in this case, the pipe constricts as it gets to the second location. So I know the second velocity should be bigger than the first. And indeed, that's what I find. The first is 20. The second velocity is 80. It's bigger than the first one. So it seems okay. Now, if this number were 10 or 5 or 8, then I would immediately stop before I move on. And I'd look back to see, how did I get this number? Did I make a mistake in calculating, or did I make a mistake in my algebra? Because I know it should not be less, it should be more. And so I'd go find my mistake. In this case, I don't see a mistake, so I move on. It's 80. Now that I know that, I now have all the information I need for my main equation, which was this Bernoulli. And so I'll rewrite it just so we remember. We had P2 minus P1 is 1/2 rho B1 squared plus 1/2 rho B2 squared. Oops, minus, I'm sorry, minus. Plus rho GH1 minus rho GH2. All right, now I plug my numbers in. I have 1/2, rho is 1,000, V1 is 20 squared minus 1,000, or 1/2 times 1,000 times V2, which I now know is 80 squared, plus rho GH1. But remember, I set height 1, since it was the lowest level, I set it to 0. So that term is just 0. Minus rho 1,000 times G 9.8 times H2, which is 15. And now I have my equation. At this point, I just have to plug all of this in my calculator to get my answer. So what do we have? Let's see, 20 squared times 500 minus 80 squared times 500 minus 1,000 times 9.8 times 15. And I get minus 3147000. Pascals is the units. Now, usually, since these numbers are going to be very large, people write them in scientific notation. And so it would be negative 3.15 times 10 to the 1, 2, 3, 4, 5, 6 pascals. Either one. I don't mind. You could either write scientific notation or just write the number out. Just know that if you're in biology or some other science, your professor would probably want you to write scientific notation just because it's neater. It's easier to look at. But for our purposes, that's not my concern. My concern is whether you can actually work the problem and get an answer. But there we go. What does this say? This says that the pressure on the top, the second location, is less than the pressure at the bottom by this much. So this isn't the actual pressure. It's just how much different the pressure is. Yeah, what's your question?
Will our answer always be negative?
No. It happens to be negative purely based on what I did with these pipes. And you can kind of see it if you think about it. If you were to have this pipe system and you put water into the pipe and then you just let it go, what do you expect to happen? Well, you would expect the water to flow in a certain way, okay, naturally. Now, how it'll flow, sometimes you can tell, sometimes you can't. This constriction really changes things. And what it changes is the fact that when you constrict a pipe and its velocity goes higher, its pressure goes down. Okay, so the fact that the pressure went down because of the constriction, that's why we found that P2 minus P1, that is the amount of difference that P2 has, is a negative difference. It's smaller by this amount. If this other example that was brought up earlier, where I'm actually going downhill, or maybe I expand the pipe, if I were to do that calculation, the number would probably be a positive number. Okay. Now, again, you can't always tell, should it be positive or should it be negative? So I wouldn't worry about that so much. If you get a negative number, all you have to be able to do is interpret it. What does that mean that it's negative? Well, what it means is, if you happen to know the value of the pressure in the first location, then you can tell me the value in the second location because it's this much less than that number. You just subtract whatever P1 is by this number and you get the value. Okay, so the negative just means it's less.
So in that situation,
Mhm.
I'm sorry. So in that situation, hypothetically speaking, if we put H at 0 and then minus 15, H2 would be negative 15.
For this situation down here?
Yes, like the same problem. But we put it in the formula, but will we switch a positive 15 for H2 for a negative 15 if the pipe went down?
Right. If we had this second example as drawn here, where we're going downhill instead, then yeah, you could call H1 0 and H2 would be a negative 15. Yeah, that's right. And notice, by the way, this talk about the height and how you have freedom of choosing what numbers you want. You could, if you felt like it, redo the calculation where H1, you called it, let's say, you could call him 10 and call H2 25 instead. And then plug all the numbers in just as before and see if you happen to get the same number at the end. And I promise you will. And it's always good to do that. You know, this is the thing I think a lot of people forget, especially as students in a science, if you're going to go into science in some way, is one of the main characteristics of a good scientist is a skeptic. Okay, you don't believe what anybody tells you. Even though they may be higher level than you and they have their fancy degrees and all of that bull crap, at the end of the day, the way to be a good scientist is to be a skeptic, because if all you do is believe what everybody tells you, well, I could be ripping you off. I could be faking what I'm doing because I have no idea about any of this stuff. But if I could speak well, if I could be confident in how I tell you these things, well, you would believe me. And you'd go the rest of your life thinking that if you constrict a pipe, the velocity of the fluid in the pipe will go up. And maybe it's actually the opposite, but you have no idea because you just have faith in me. Now, obviously, I'm not bullcrapping you with this stuff. I'm being honest. However, just in general, if I were to tell you, like I did with these heights, that it doesn't matter what you choose for the values of a height, as long as one is 15 more than the other, well, you want to prove it to yourself. Do it yourself at some point when you have some free time, you're working on practice problems, whatever it is. Say, let me see if this guy knows what he's talking about. And you actually plug the numbers in. And that'll allow you to have a lot more confidence in whether that's true. And that's true of everything. Like I said, anytime anybody goes on the news or is on TV or whatever, and they may be famous and they may be high up in their particular field, and they just tell you something, if you have the ability to, you should always verify it, because those people can be wrong, just as I can be wrong. Obviously, I could do bad arithmetic, plug things in my calculator poorly, or I just may not know this theory too well, and I'm forced to teach the class, and so I'm kind of faking my way through it. You never know. So it's vital, if you're going to be a scientist of any sort, not just a physicist or an engineer, but if you're in a biology lab, or you're a chemist, or you're going to go into some data analysis or whatever it is, always verify what people are telling you. If, now sometimes you don't have the ability because you don't have the data they used or the high tech equipment, but at least you could try to go research what they said and see if it actually is true or if they're making it up. Because one of the things you find, and this is kind of a rant, but what you find, especially in science as it comes out in the news or on TV, is the scientist is never wrong, right? Even when they're wrong. So they'll say something, they'll say, we think the theory is that the first humanoid on Earth, the first human, was 50,000 years ago. And so for hundreds of years, people believe this. And then one day they find evidence that that's not true, that maybe it was 500,000 years ago. They find, fossilized or whatever. And shoot, we were wrong. So now the scientist comes out and says, yes, we were wrong back then, but now we know it was actually 500,000 years ago. So now the scientist who was already wrong once is now again the right. They are the ones telling you what is correct and what's not. But again, they may be wrong still, they just don't know it. But that's the good thing about being a scientist when it comes to, media type things, is since they're the experts, they're always right. When they fix a mistake, they're now right again. There's never a time where they're wrong. And there's reasons for this, obviously, but what it shows you is to always be a skeptic if you're going to be a scientist. If I tell you a physical theory and you have the ability to test it in some way, go outside and throw a baseball and see if it uses a parabolic curve, or kinematics, you could figure out how long it'll take to drop a rock from your shoulder height. And the math says this, we'll do it and see, does it take 1.5 seconds or whatever it is? Just little things like that. And it's more and more important as you get into your career to definitely verify things, because that's when it's truly vital. But just always be skeptical. And so one of the ways, as I was saying here, is I claim you could choose any values for these heights as long as you stick to the requirement that height 2 is 15 above height 1, and see if the math actually shows that's true. Once you see it for yourself, you believe it. And now you could use that fact later on. But if you just believe me and I'm lying to you, then you go on a test and you use it. Well, I could be an a-hole and say, this is wrong. You're getting the wrong answer. Yeah, but you told us we can do this. Well, you should have known I made a mistake back then, or something stupid like that. That actually happened to me as a student in a math class in high school. The teacher told us to solve something a certain way. And so I did it on the test exactly as she said, and she marked it wrong. And so I confronted her. I said, hey, but you showed us how to do this. And this is, look at the notes. This is exactly what you did. Said, yeah, I made a mistake, but you should have been able to catch that and fix it. And so I lost points. And the same thing happened in college in a physics lab. I had a graduate student was teaching the lab, and she was from Romania, and she had very poor English. And so I think she would misunderstand questions given to her just because it was hard for her to follow the English of what the students were saying. Well, I noticed that what she was telling the students was wrong in how to do a certain calculation. And so I told the student after she was done, I went to him and I said, look, I think she was making a mistake. This is actually the way it should be done. And of course, they didn't believe me because I'm just a stupid student with them. What do I know? She was the teacher. And sure enough, when we got our lab reports back, they got the stuff wrong because they did the method she said to do. And then they were all aggravated about it. And I said, look, I told you, I tried telling you that she just made a mistake. So anyway, it's kind of a rant, but I think it's an important piece of advice that we forget. It's very easy for us to go down this fallacy of trusting the experts on absolutely everything without verifying anything, just having faith. But as a scientist, you have to do the exact opposite, because that's generally speaking where new things are formed. When you don't believe something is true and you go to try to show that there's a flaw, that's when new physics is formed, or you find new theories of evolution or new theories of biology, or whatever the case may be. All right, so all of that said, this is how we do these Bernoulli equations. You're given the problem, have some kind of image either drawn for you, or in your mind, you visualize the pipes. You say, okay, what's going on? Do I need all of the terms of Bernoulli? If you change heights, then you need the height terms. If you change the size of the pipe, you need the velocity terms. If something like that is not there, if you don't change the size of the pipes, then you can just cancel out the velocity terms. They go away. Or if the pipe doesn't change heights, if it just stays straight, then you could just cancel out the height terms. So anyway, you have your Bernoulli. From there, you see, do I know all the numbers I need? If you have all the numbers, you plug them in and you get your answer. If there's something you don't know, like in this case, we didn't know velocity 2, then we have to calculate velocity 2. In this case, we use continuity to do it. And every time, if the velocity is the thing you're looking for, you're going to use the continuity equation. So you use it, you calculate your new velocity, then you say, does this make sense? Should it have gone up or should it have gone down? And what did I get? Hopefully it makes sense. And so, okay, good. I use that number. And then I plug everything into Bernoulli, being very careful about little things like making sure my units are correct. I'm not using centimeters anywhere. Everything's meters per second or meters, kilograms per cubic meter, all of that, all of those units. Plug everything in, calculate it out, and I'll have my answer. Okay. The only things that can change are, what's the pipe system? Is it going uphill? Is it going downhill? Is it expanding? Is it contracting? All that kind of stuff. One thing to look out for, which happens a lot, is a problem. Let's say it's kind of a text-based, there's no picture. So you're reading the problem and it says something like you have a pipe, which is 20 centimeters in radius, water's flowing through the pipe. The pipe extends for 5 meters. After those 5 meters, it then goes uphill to the second floor, which is 20 meters above the ground. Once it's up there, it then expands another 15 meters before it constricts to this new radius. And then find the change in pressure. Well, there's a lot of information in that problem that you don't need. You don't need the fact that the pipe extended out 15 meters. Who cares how long the pipe is? There's nothing in Bernoulli that has anything to do with how long the pipe is. All you care about are, does it go uphill or downhill and how much? That's the height. Does it expand? Does the radius get bigger? Does it get smaller? How far out it goes or anything like that is completely nonsense to your calculation. And I've given a problem like this several times in past semesters, just to make sure the students who are working the problems have an idea of what's important and what's not. And so if a student tries to use information about how long the pipe is, well, I know they don't understand this concept. The length of the pipe makes no difference. The size of the pipe does. And does the pipe go uphill or downhill? Those are the things that matter. But if my pipe, travels from one house to another, which is 30 meters away, well, who cares about that? That doesn't change anything here. So you just ignore that information. So be careful about that if you're looking at a practice problem or a homework problem or something, that some information may be in the problem that's not necessary. The only information that is necessary is the radius, how big is the pipe, and the heights. And then, of course, what the pressures are, if it's given the pressure. All right, so any questions about this?
I have a question.
Yes, ma'am.
So, I see how you found the answer, but as far as for the P1 minus P2,
Yeah.
is there something we're supposed to do for that remaining part of the problem?
No. Basically, what the question is asking is for this thing, which you could call it delta P, you could call it the change in pressure. That thing happens to be P2 minus P1. So you just get it over there and that's all you care about. Now, what might happen is there could be some other problem where I say, if the pressure at the first location is 1 times 10 to the 5th, then what will be the pressure at the second location? Well, now I don't want the change in pressure. What I want is P2. I want the value of P2. Well, if that's the case, then just bring P1 over to the other side. So now there's a plus P1 over here. But you know that number because it's given in a problem. And now there's just P2 on the left. So P2 equals blah, blah, blah. So it all depends on what the question's asking. Here, I'm asked to find the change in pressure, which means get on one side of the equation this set of terms. And when I have that set of terms, that's just something that I call change in pressure. I don't care what P2 is. I don't care what P1 is. But P2 minus P1, that thing is this number, and that's what I want. Okay, so does that make sense?
Yeah, thank you.
Yeah, it's a little weird because we're used to with algebra, you have one variable on the left and everything else is on the right. Here we have two. It's kind of weird when you're not used to it. But if you just think of those two things together like this as one concept called change in pressure, then you could think of it like it's just one variable. Even though it's really two sitting there, it's just one thing for us. Any other questions? All right, so before I let you go, and I know it's already end of class, firstly, there is a homework assignment posted to Canvas on this stuff. I think it's 2 small questions. It's due Wednesday, so there's plenty of time to do it, but I would suggest, of course, doing it over the weekend just to get it over with. And it's on this material, so we've seen enough example problems to be able to work those homework problems. So that's there. Be sure to do it. Also, as usual, these recorded Zoom things are posted on the Canvas, and these little notes that I'm writing here, they're always uploaded. But also last year's recorded lectures on this material is also uploaded, so you could watch those too if you want some more examples. Next class, Monday, we will start into the second half of fluids, which is first the pressure depth relationship, which just is studying how as you go further and further down underwater, you feel more and more pressure, which is why, we can't explore the oceans too well, because the deeper we try to go, the more pressure there is, and it starts to kill us, and it even starts to crush submarines and fancy equipment. But we want to know exactly, if we go down 100 meters, how much pressure are we going to feel? Can we survive? And stuff like that. So that's the first thing. The second is Archimedes principle. And that has to do with buoyancy. How much force is there making you float? Or is there not enough force so you'll sink? And so that's Archimedes principle, which we'll discuss. So that's what we'll start on Monday. In the meantime, of course, work on the homework problem. If you have any questions on it, feel free to email me. But other than that, if you have no questions, you're free to go and enjoy your weekend.
Oh, Dr. Rajman,
Yes.
I actually I had to turn in homework again because the second part of the problem
Mhm.
I learned about now that I how to conduct the Bernoulli's equation with adding heights. I completed it again, so now I feel like I'm better. I feel more confident with this new submission.
Okay, yeah, no problem. I have it set for multiple submissions, so when I do go to grade it, I should just see the latest one.
Okay. Thank
All right, no problem.